Okay, so our first video on cumulative distribution function, CDFs, and there'll be another video after this one, but here's an introduction. So we have this thing called the cumulative distribution function, or sometimes cumulative density function, capital F of x. Now it talks about the probability that a continuous random variable x has less than or equal to little x. So it can be expressed in various notations, depending on what source you're reading from. And whoops, too far. There you go. So it can be expressed as the probability from x up to some maximum value c for some density function, from the bottom to the top limit. And it can also be expressed as the probability of the random variable x being less than or equal to x. Now that's equal to a function. Now t is the integration variable here for the density function. Okay, we'll have a look at that in a minute. So that's the variable of integration for the density function from some value c up to a certain value of x. Okay, so we have the probability density function f, as I said, would be between some interval starting at c. The relationship between the two is particularly interesting and important. So we have here the probability density function that we've seen in the past. And as x increases, we get an increasing area. If we plotted the size of that area onto another graph, we'd get a cumulative effect from 0 up to some final value. So they're two different things, and that's your CDF, your cumulative density function. Okay, so capital F of x, the cumulative density function, that's this one here, at a particular value of x, gives the probability that the random variable capital X has a value of less than or equal to x, so at most x. Alright, so that's what accumulates. So as you get further and further, that accumulates. And we use the fundamental theorem of calculus in this work, and we can demonstrate that the derivative of the cumulative density function gives us the probability distribution function, or the probability density function. Of note, if we go back to basics a little bit here with integration, the integral for some probability between a and b exclusive is the integral of the probability density function between b and a. Now, because it's a density function, specific values have a probability of 0. And we've seen that in the past, because they create 0 area. If you like, the width of the graph is 0, because a single point has no width. It's a bit of a different way of thinking about it. So we get some interesting results out of that, which we use subtly in these questions. So the probability from a through to b for variable x is the probability of a through to b excluding a. It's because a itself has a probability of 0. We saw just on the line above there. Okay, we saw that there. And if we did the same thing except for vice versa, we excluded b, same reason. And that, if we put them together, this, interestingly enough, equals that. And you'll see, hopefully, as you do these questions and watch the video, you'll see the use of that. So this means also that we can break things into parts here. Okay, a through to b is a through to c, and excluding c up to b, so we don't count c 2 times. Okay, and so we can break things up. A few stipulations here. So the CDF, in other words, uppercase f of x, must be a non-decreasing function, so it always increases. That is, f of a is less than or equal to f of b. Alright, so that's alluding to that there, where a is smaller than b. As x approaches negative infinity, the CDF function approaches 0. Alright, and the limit as x approaches negative infinity of capital F of x is 0. Vice versa, except for that as it approaches infinity in the positive direction, the CDF f dash of x capital is approaching 1. It equals 1 at the limit. Okay, and so we can break things up, and given that we have x is less than or equal to some point b, we can break that down. Now that would be from x up to a, like we said, if a is less than b, plus a through to b excluding a. But if we rearrange it, we can find that by going x less than or equal to b and minus the probability of x less than a. Alright, so we can find the probabilities of these things by using the integral of that, because as you know, these are related to a rule of integration. Now, to clarify all of that I've gone through rather quickly, we're going to do a couple of tasks now. The time variable x seconds takes for a student to complete a puzzle is a random variable with a density function given by, so be clear, this is the density function, hence we're talking about little f of x. Alright, and that's the interesting part of it for us for the reasons we've seen in the previous videos. Find capital F of x, that's the CDF, the cumulative distribution function of random variable x. Okay, we'll do that first, and so in general we've got capital F of x is the probability that we have big X less than or equal to little x. Okay, now that equals, in general, from negative infinity through to whatever the x is, for f of t dt, where t is the integration variable for the density function. Okay, so t is the variable of integration. Okay, and that's for the probability distribution function. Okay, and so we start from there and we continue through the process. Now we've got to make this more specific. So here, in this case, we've got capital F of x will be from, now see how it's 5, alright, so it's 5 through to whatever x is, and that would be for f of t dt. Okay, and then we have, using the given function above, in regards to the variable t, we would have 5 over t squared. Okay, so we have 5 over t squared dt from 5 up to x. Remember, we're trying to generate a function here, so our answer is going to be a function. Okay, now using your integration, okay, you would have, I'm leaving out the specifics of the integration because you should be all over that by now, but you might have to pause it and do the integration yourself. Okay, and that rearranged is 1 minus 5 on x for x greater than or equal to 5. Okay, so that's the function. Now that we've generated that, we can use that to find a few things. X is less than or equal to 7. So let's do that one. X is less than or equal to 7. Okay, now in the density function, the CDF, the cumulative density function, that's the same as f of 7. Alright, now if we sub that into our function we've just generated, we have 1 minus 5 over sub in 7. Alright, 5 over 7, and that's 2/7. Okay, alright. And the second one is the probability that x is greater than or equal to 6. We have 1 minus the probability that x is less than 6, for the reasons I stated above, which is 1 minus f of 6, which is 1 minus 5/6, which is just 5/6. Last part, we have the probability of between 10 and 20, and explain the reasoning above there. And we have probability at x is less than or equal to, that's x is less than or equal to 20, less than or equal to 20, minus the probability x is less than or equal to, well, just less than 10 actually. We don't want to count 10 twice because 10 will be counted in that one as well, you see. So it'll be, doesn't matter because it's f of 20 minus f of 10, capital F of 10 anyway. And so that comes out as 1 minus 5. Well, it comes out as a quarter anyway if you sub those in. Alright, f of 20 and f of 10. Finished.